IARPC is associated with the Federal Arctic Research Plan. So there's a plan, and there are teams to shepherd the objectives of that research plan. So the modeling team has been around longer than the 5-year plan. Our goal is is focused on enhancing understanding of the integrated Arctic system through the use of regional and global Earth system models. So we welcome the modeling community to this meeting. I see a lot of familiar names, and and a lot of some new names as well. So welcome everyone to this meeting. So in this meeting, we'd like to look at applications of machine learning to Arctic climate topics, and in particular, for our purposes, methods that combine machine learning techniques and traditional Earth system models to address complex research topics. So without further ado, we'll go to our first presentation. So Zack Labe is a postdoctoral research associate with the program in Atmospheric and Ocean Sciences at Princeton University and NOAA Geophysical Fluid Dynamics Laboratory. And the title of his talk is Explainable AI Approaches for Evaluating Climate Models in the Arctic. Zack, welcome.
All right, hopefully you can all see my slides. Hi, everyone, and thanks for having me. It's my first time in this particular meeting, and I'm really excited to chat. I'm interested in a wide range of sort of climate change and variability topics, especially related to polar regions. And one area that I've really gotten interested in is how we can leverage some of these new advances in machine learning, specifically explainable machine learning, in understanding new things about climate science. And so I realized this group, out of any group, knows that the Arctic is warming really fast. But as some of you might know, I really like data visualization. So I thought I'd start off one, of course, showing observations of the Arctic for every year over the satellite era, of course, showing that the Arctic's warming. So one of our challenges, as us trying to understand Arctic climate and going forward into the future is, of course, trying to understand how well our models are capturing that. So what you're seeing here is a line graph that's showing the temperature from observations in the two reanalysis products from 1950 all the way through present, compared to sort of a large collection of large ensemble simulations from fully coupled climate models extending all the way through 2100. So you can see that our climate models, at least for capturing something like the mean temperature, are doing quite well. But of course, we know that there's a lot more to, evaluating a climate model than just looking at something like the mean. So traditionally, we, of course, have a whole toolbox of methods to evaluate how well our climate models are doing compared to observations, especially during, the satellite era record or during the historical period. And traditionally, we do things, pattern correlations or some type of error metric. But this work was done with Libby Barnes, her and I, from about 2 years ago. And we sort of posed the question, okay, we have these sort of standard set of go-to methods and sort of diagnostics for evaluating climate models. But what about something like machine learning? And we know that machine learning, it likes a lot of data. And machine learning is also really good at capturing regional patterns. So could we use this tool to our advantage in providing some sort of new way of evaluating climate models with observations specifically into the Arctic? So that's where I'll be going in this talk. And I always like to point out that machine learning is not new. It's often a buzzword, and now AI is in the evening news every single night. But, I've had a lot of fun sort of diving back into the literature, looking at machine learning in sort of my area of atmospheric science and climate science. And you can find examples of neural networks similar to what we use now that go back all the way to the 1960s. So I think it's always important to point out that machine learning is not necessarily a new phenomenon, and that many of these methods have been used for decades. And I really think of how we can use machine learning for climate science sort of falling into sort of 3 branches. We can use machine learning for sort of improving our climate models. So we could use it for new parameterizations. We can do things like try to make our climate models run faster on HPC systems or design new emulators for specific processes. But the topic that I'm really interested in is a bit different. I'm interested in this idea of do something new. So really trying to understand, can we use machine learning as just another tool to learn new phenomena or physical phenomena in particular about the climate systems, specifically related to climate change and variability? And so I want to start off really simple to get us started and ask you a question to think about. what is the actual temperature of Earth and how do we go about evaluating that? So we can look at, observations. So we can take the mean over a global map of data and plot a time series from observations. So that's what you're seeing here. And then if we wanted to, compare it with a climate model, we might look at, let's say, one ensemble member from a global climate model. And of course, it does well and it sort of captures the long-term trend, especially since 1980. But of course, it doesn't capture the exact interannual variability. So one, real exciting phenomena in my view that's been around now for a little while is running large ensembles. So you essentially tweak the initial conditions just a little bit, maybe perturb the atmospheric initial conditions by a small round-off error. And you can run, another ensemble member again and again until you sort of capture the full range of, hopefully, the full range of internal variability compared to observations, which better can allow us to sort of understand this question about what's the global temperature. Where, and this is just to go over if you're not familiar with large ensembles, that these data are really unique statistics where you can take the mean over those ensemble members to better understand like the forced response. You can then look at the range of all those ensemble members to get an idea of the noise in the climate system, that internal variability. So you can do lots and lots of statistics, like remove the climate change signal, and then you just get a flat line, that's the noise. So I think, in addition to providing a lot of data, you can get really useful statistics about climate change and climate variability. And so what I'm really excited about, all of these types of statistics, like getting anomalies and noise, is that this also provides us a lot of training data for machine learning. So the way I often sort of think about it for machine learning is that we can use individual ensemble members to, for example, train our model where we can get a different realizations where it has the same force response, but it has different noise. We can then set aside some other ensemble members for validation data. And then finally, we can apply sort of these extra ensemble members for testing data to give our model sort of out of sample data. And we know that there are many of these large ensemble simulations. So again, lots and lots of data, which is always good for something that's data hungry like machine learning. And so at the crux of machine learning, I like to think of it really, really simple in that it's just lots of data that you're inputting and you're inputting it to some statistical model, and then you output a prediction. And so, that's sort of how I like to think of machine learning, just sort of some fancy statistics. And now I want to return to sort of the climate maps and, question I asked earlier. And we know that when we work with sort of gridded data, we have some characteristics. And we found that by asking machine learning models really simple questions, we can actually use some new techniques from explainable machine learning to, again, understand something new about the climate system. And one of the questions we decided to ask was a pretty simple classification problem where we decided to input, a map of a certain variable, let's say for every temperature map for every year into a neural network from many different climate models. And we would ask the neural network to be able to identify which climate model was associated with which map. And that's the general direction I'll be going to describe this work we did. And so we started off with global maps, where again, we took a maps of temperature, annual mean maps. We input it into a neural network. Again, you can just think of this as some statistical algorithm that's good at understanding sort of nonlinear spatial features. And then we ask which climate model was associated with each map. And so this was a classification problem. So essentially we had sort of 7 climate models associated with this particular problem. And one reason that many people are hesitant about machine learning methods is that they're often foreseen as sort of a black box. So it goes into this fancy statistics and it produces some prediction or classification, but we really don't understand, how it made its prediction. And so this is the part that I'm really interested in, and hopefully will convince you that machine learning doesn't have to be a black box, and that there's some really exciting techniques from something called explainable machine learning or explainable AI from the field of computer science that we can actually use to understand what's going on in this statistical algorithm. So to sort of give an example, not related to weather and climate, I'll show you an example from a image classification problem. So I want to imagine, you have a really simple, let's say, neural network, and you're inputting images into the neural network. So in this case, you input an image of a wolf, the neural network, it gets it correct. So then you might want to ask, okay, how did the neural network know to make this prediction that it was a wolf? So this is where we can apply one of these explainability methods, and I'm just showing one method here. There's many. And this is called layer-wise relevance propagation. And what it outputs is a heat map. And it tells you what areas of the image were most relevant or most important for the neural network to make its prediction. So in this case, you can see that sort of the nose of the wolf or the ears of the wolf were really important. So the brighter yellow colors were what was most important from the image to make its classification. Here's just another example. Here's an image of a volcano, and the neural network again made a correct prediction. And then we can turn to this layer-wise relevance propagation, this explainability method, to look, okay, where in the image of the volcano was most important. So in this case, the neural network was really using information about like the cone of the volcano between the sky and the mountain to make its accurate prediction. So we can apply this type of methodology, this explainability methodology, to understand the Arctic and ask this question about, can we use this to classify data with climate models and then use explainability methods to figure out how this happened? And so in this case, we now, instead of thinking about global maps, we're now going to be turning to the Arctic. So in this neural network, we took annual mean maps of temperature, where each grid point from the map is part of this input layer. If that goes into a neural network with some hidden layers and nodes, that's where all the excitement happens. And then it outputs what climate model was associated with each map. And maybe not surprising, this is actually a really simple task for a neural network. It can quickly pick which temperature map is associated with each climate model, even considering that, it's seeing many realizations of internal variability. And that's because the neural network, it's pretty good at picking out mean state biases between the model. But where we're going with this is now we can, we have this neural network that's trained on the climate models. What happens if we input observations? In essence, if we input observations, which climate model would look most similar to observations for every single year? So that's what we did. So then we trained this neural network on all these climate models, and it's done quite well. So now we throw in this out of sample data coming from different observational products. And again, it's annual mean maps over since 1940 all the way through present. And then what happens is we can actually sort of get a prediction for what climate model was, quote, most similar to observations for every single year. So there's something, this is a bit more technical of a term, which I apologize for, but there's something called the soft max operator. Essentially what that means is it sort of scales the output so that you get this value called the confidence. So when you input, let's say 1 year from observations, it's going to output the confidence that it's from each particular climate model. So what we're looking at here is we're trying to find which climate model had the highest confidence. So in this example, you can see the confidence listed here for each of the climate models, and then I can rank them according to the highest to lowest confidence. And then so we can say that the output or the class, the model had the highest confidence was, quote, most similar to observations for this specific year. So for this example, which I've just shown for demonstration here, it was the CANISM model, so the Canadian large ensemble model for that particular year. So then what we can do is we can produce, metrics like this. So now what you're looking at, instead of just one single example that I showed you here, you're now looking at heat map of the rankings for every year from 1950 all the way to near present for each climate model. So if you see the number 1, that means that that climate model was picked as the most confident, most similar to observations for that particular year, and then so forth. And if you see sort of the black shading here, that essentially is in essence that the neural network said it was below random chance that it would be that climate model. So essentially, we can see that for the most part, you can see the top 3 climate models compared to observations are ranked here. So you might say, okay, we already have metrics, error metrics that can compare, observations to the models and calculate things like RMSE or mean absolute error. How does this differ? So this is where we can turn to explainability techniques and try to understand, okay, how did the neural network know to classify which is which? And what's really exciting, at least to me, is that for this explainability method, you actually get one of those heat maps for every input. So what I mean by that is if I'm inputting, let's say, 50 years of data, I then get 50 of those explainability maps. So I can understand each individual year and figure out, okay, in each individual year, what were the most relevant regions? So you can do interesting things like take, composites over different time periods. For example, I can focus on like the greater Arctic amplification era from the last 20 years and try to figure out which model was most similar to observations. And then I can look at older periods to figure out, essentially which model was closer to observations pre, Arctic amplification. So that's what I'm showing here with these little maps. So you're seeing that a relevance map for each climate model. Any area that's real bright indicates that that region was a really important region to distinguish that climate model. So as an example for this one, if you see that the Cicero model is really lit up, it's quite bright. And that's because that climate model has a bit of a cold bias within the Arctic and has a bit greater sea ice, especially towards the Barents Sea and the North Atlantic Ocean. So the neural network was able to pick up that particular region was an identifying feature. So anytime, it saw that there was, colder, mean state, specifically in those regions, it was able to know, okay, that map came from that particular climate model. So then you can do things, take the differences between these two different periods, and you can calculate things like the greatest variability and relevance. So I think explainability techniques for machine learning really offer an exciting opportunity to try to understand more of the physics, that we're often interested in, the mechanisms, specifically mechanisms that may differ or be similar between climate models and observations. So I just summarized, given the limited bit of time from this particular paper that came out in AGU's Earth and Space Science Journal, which really goes into more details about this method. I'll point out just lastly that the real, difference between this method is not that it's, better than our other types of diagnostics for model evaluation, but it's providing us something different because again, the advantage to the neural network is that it's really learning spatial information. It can leverage different regions side by side or interesting covariance between, let's say, models and observations. And if there's time, I'm happy to have questions or discuss this at the end. So thank you.
Thanks very much, Zach. So if you have a question for Zach, you can unmute and get my attention, or you could go for the to raise your hand with the that's under the reactions button on Zoom, or other ways to get a hold of me. So Zach, with these heat maps, so in classical analysis, you might do principal component analysis, which would show the orthogonal variations of the principal variations of the of a given field. But my understanding of a heat map here would be that it's actually on a more granular scale. It's looking at the intrinsic features that are distinguishing the particular models and things like that. Could you expand on that a little bit?
Yeah, well, I think that's exactly, what it's doing here. It's looking at the different features and it's leveraging them across, if the North Pacific varies and the North Atlantic vary, it can look and understand those types of relationships. So it's doing a bit more difference than sort of calculating a time mean or calculating point by point statistics. There are tricks with explainable AI, so it's not a causal method. So it can provide us information of like, where it's looking to make, in this case, a classification question, but it can't really tell us, the question about why, which we're often interested in. So explainability methods can give us a little idea of what's going on in the black box, but it certainly, can't provide us the entire story.
Okay. We have some questions in the chat. One is from Vladimir Alexiev. Vladimir, would you care to unmute and ask your question?
Oh, sure. Hi, Zach. So I think that model and ops have their independent properties in terms of variability and trends and cause and effect kind of a thing. So I am not sure why is it so important to look how similar models are to observations in any particular year.
Yeah, hi, it's great to see you. Yes, no, I agree. Given internal variability, we wouldn't expect a model to capture exactly from year to year. And what I didn't have time to go into is that this method it's really what it's doing is it's actually extracting sort of the force signal per year. So it's seeing, multiple ensemble members, multiple realizations of internal variability. So what the method is actually doing, it's actually really trying to, it's extracting sort of the forced response. It's learning it in each model and sort of comparing that pattern with observations. So it's a bit complicated. And I agree with you that it's not really an interesting question about it per year basis, but more the longer term. So if we see any trend, we did some other experiments where you can remove the mean of the maps to or detrend data and get some other interesting answers. But I agree with you, per year it's not that interesting, but over decades basis, especially as Arctic amplification gets larger, that's when the neural network is particularly useful at extracting the force response.
So in a particular year, one model could be doing an El Nino and the other one could be doing a La Nina or something like that. But the neural network method would be able to would still be able to distinguish individual models, and it would be able to understand, what's going into the Arctic temperatures. Then is that a fair statement?
Exactly. Yes. I think I've done other applications with neural networks, and yeah, they're a really, really good tool, especially if you don't have a large ensemble. They're really good tools at learning the force response and using that pattern information. And sometimes it does look different than what, if you did have an ensemble mean. So those are interesting questions, whether that's physical or not. But yes, that was a good summary.
Okay, Mike Steele also has a question in the chat. Mike, would you care to unmute and ask your question?
Well, maybe my question's already been answered. I don't know. I just honestly, I just don't get it. I mean, you showed pictures that looked like a difference of a model prediction of surface air temperature relative to an observation of the same thing. And why can't I just do that? I don't understand what the machine learning is different from that.
Yeah, so we do spend time comparing it to just computing bias, in which model has the smallest bias compared to, what we would do without something fancy machine learning. The advantage here is about this force response, which I only had 15 minutes to present. So I didn't get too much time to mention it, but what it's able to do is it's able to learn this forced response for each model in a single realization of an ensemble member in essence and compare that with observations. So, and again, it can do things beyond a point-by-point statistics, or it also does it on time evolving forced response rather than sort of over epoch. So I'm not definitely, this was an exploratory work. There's a lot of questions of whether machine learning might be an interesting new diagnostic for models. Definitely not claiming that it, replaces anything or is better than anything. Just something to give it a try and see what would happen in essence.
Go ahead, Mike. Do you have a comment or feedback on that?
No, I guess I better read the paper. Thank you.
So there is a lot of interest in climate analysis on fingerprinting. I would assume that machine learning methods would be particularly effective for doing that. Perhaps that was hinted at in your example here. Would that also be fair?
Yes, so fingerprint probably appears in the paper. What it's learning is its fingerprints of climate change per year basis for each climate model, and then comparing that to observations.
Okay, very good.
Thanks.
All right. In the interest of time, we'll go on to our second presenter here. Lauren Hoffman is a postdoctoral researcher, most recently with the Earth and Life Institute at UC Leuven, Belgium. And her talk is Machine Learning as a Tool to Predict and Understand Sea Ice Motion in the Arctic. Lauren?
Hello, everyone. I'll get going on sharing my screen. All right. So first of all, I'm glad Zach went first. Because Zack, at one point in your talk, you said you hope you convince us that explainable machine learning is a good tool. And in fact, in the second year of my PhD, you convinced me. I saw your work and I moved forward with those methods in the work that I was doing. So thank you for that. It's cool to be here and to talk with you. But the topic that I focused on is using machine learning as a tool to predict and understand particularly sea ice motion in the Arctic. And this work was done with the collaborators listed here at Summit Scripps, Washington, Texas, and funded by ONR. And as was mentioned, now I'm at UC Leuven in Belgium, and I'm working on a similar project using machine learning as a tool to predict and understand rapid ice loss events in the Arctic. So won't be talking about that today, but if you have questions, feel free to reach out. And so the first thing that comes up is sort of why turn to machine learning for this problem, for predictability of ice motion. And the reason being is that these machine learning models have fewer complexities and a lower computational cost than the traditional physics-based models, particularly when it comes to sea ice dynamics. This image here is just showing some of the many physical processes that are now included in the state-of-the-art numerical sea ice models. And we see there's a lot going on, a lot of conservations that need to be taken into account, parameterizations, estimations of these physical processes. And so machine learning can just lower the complexity and improve the computational efficiency of this. And so a larger part of the work that I did here was to use a machine learning model as a surrogate to parameterize the sea ice dynamics part of a numerical model. And I didn't work on that side of things particularly, but if you have questions, I can direct you to those people. But I'm more focused on the understanding side of things. So first of all, can we build a skillful machine learning model? But what can we learn from that machine learning model? And because these models are not prescribed a certain set of physics, we can actually draw information from that data and perhaps learn about some physics that has not yet been elucidated. And so that is what's done here. And the particular physics that I'm interested in is this relationship between sea ice motion and wind speed. And so this study here done by Maeda et al. In 2021 is showing that sea ice is becoming more responsive to wind forcing. This thing called the wind factor, the ratio of sea ice speed to wind speed, is increasing. And we can see that in the first image where we just see these trend lines, the blue and the red representing a summer and a winter trend line, both positive slopes. So that wind factor is increasing in time. And then in the map, we're looking essentially at the slope of that line plotted at each point throughout the Arctic. Largely, we see red, we see this positive trend in the wind factor. Or in other words, again, that sea ice is becoming more responsive to wind forcing. And so this study was done with a simple linear regression just between ice speed and wind speed. And the thought here was, well, if we apply one of these nonlinear neural networks, can we draw more information from the system and learn more intricacies about how that wind factor is changing, when, where, maybe why. But so this work is sort of divided into two parts. First is the predictability side. Can we build a skillful model to make one-day predictions of ice motion? And then the second part is this understanding sea ice motion. And this is where we take this explainable machine learning methods and try to dive into that black box nature of why did the machine learning model make the predictions that it made? Where were the inputs relevant or important in predicting the output? Specifically, again, where was the wind relevant for driving the prediction of sea ice motion? And so when we build a machine learning model, we need to understand what inputs to put into the system. Here we're making one-day regressive predictions of ice motion. And so we turn to physics for this. This momentum balance for sea ice indicates that on these one-day timescales, the main drivers of ice motion are the wind forcing, the ocean currents, and the internal ice stresses, the second and fifth terms in the equation, and this crude depiction of some sea ice. And so when we build these models, we build them from satellite and reanalysis sources. So we don't necessarily have, a satellite product that shows the ocean current at every location or the internal ice stress at every location. And so we use some variables as proxies for these. And in the end, we build this machine learning model that makes one-day predictions of ice velocity from inputs of present day wind velocity, previous day ice velocity to represent the persistence of the system, and previous day ice concentration to represent those internal ice stresses. And here, the specific machine learning model that we use is a convolutional neural network. And we choose this model because a CNN works really well for images or image-like data sets, such as these gridded mapped products, because within the architecture of a CNN, there is a convolutional filter that runs over locations in space and looks at those non-local interactions. So we can get a lot of information from that. And so the first side of this was predictability. Can we make a skillful model? And in order to test this, we train the model, here are the inputs, here are the outputs, and can you learn relationships between these? And then we hide a subset of that data and we say, okay, here are the inputs, make a prediction of the outputs. We know what those outputs are supposed to be, and we look at the difference between those. Particularly here, we're looking at the correlation between what the model predicted and what actually happened in the first map. So correlation, a perfect correlation would be 1. We largely see that the CNN is doing pretty well at predicting ice motion on one-day timescales, particularly in the central Arctic, with some decreases in performance in the coastal regions and some of the peripheral seas. But largely, we're saying, yes, the CNN is making skillful predictions of ice motion. And the second image here, we looked at a comparison between the CNN's predictions of ice motion and predictions made by a linear regression model. So here, red indicates regions where the CNN outperformed the linear regression or made predictions that were closer to what was expected. And blue is where the linear regression outperformed the CNN. Largely, we see red, which means largely the models that incorporate these nonlinear relationships between the inputs and the non-local interactions are capturing important information, i.e. that CNN is capturing information that the linear regression is not picking up on. And so that's the predictability side of thing. Yay, we made a skillful model. Can we move forward and use that model to understand that relationship between wind and ice? And so here we employ these explainable machine learning techniques that Zack went into a lot of detail about in order to interpret where each input is relevant in the machine learning model for predicting that output. And so again, we get one of these relevance heat maps for each input, for each time step. And because we're making a regression prediction here, each grid point actually provides an entire map. So it says at this location here, what is the map of the input that was relevant in predicting that particular grid point? And so I like to think of this explainable machine learning. Linear regression is sort of a simpler form of machine learning. It's a statistical model. So I like to think of the explainable machine learning as looking at the A, B, and C parameters of a linear regression equation. Say we had one equation at each grid point throughout the Arctic, and these parameters are giving us some indication of how much of the variance is explained in the output by each of these inputs, or how important, how relevant are each of the inputs in predicting the output. And so when we started to dive into this study, there are several different explainable machine learning methods that particularly we wanted to focus on this layer-wise relevance propagation method that Zack had talked about. And we wanted to do it on a domain integrated form. So as I mentioned, with layer-wise relevance propagation, we get for each grid point of the output that we made a regression prediction for, we get a map showing this is the map of where that input was important for predicting that output at that location. If we wanted a map for where the input was important for predicting the entire Arctic, we could take all of those maps and integrate them to get a map of this is where this input was important for making a prediction of the entire Arctic region. And so that's what we mean by domain integrated. And this domain integrated form of the LRP was sort of novel for this application. And that's why we wanted to compare it to all of these different methods. So in this paper that is about to be submitted It's a comparative analysis of these different explainable machine learning methods to gain trustability in this layer-wise relevance propagation in a domain integrated form, applied to a regression problem. And so we found that, yes, we can trust this layer-wise relevance propagation. But for the remainder of the talk, I'm actually going to switch over to looking at linear regression and sort of build a case for why we would want to turn to this LRP instead of looking at linear regression parameters. And so, as I've said, we're interested in looking at this relationship between sea ice speed and wind speed. It's been shown that ice is becoming more responsive to wind with a simple linear regression between just those two parameters. And here we're going to apply a multiple linear regression and look at the trends in this wind factor, or that linear regression parameter for wind speed. And so what we're showing here, the first image is just the ice concentration. The blue and the red lines represent the trend in minimum and maximum months of ice concentration. We see negative slopes. We all know this. The ice is declining in the Arctic. The second image is showing that linear regression parameter for wind speed, that wind factor, which we see a positive slope in both the red and the blue lines. That wind factor is increasing, confirming results from Maeda et al. And then lastly, we look at the ice speed here. We also see a positive slope in the ice speed. And so the link between these three factors is called the free drift mechanism, whereby we have a decrease in ice concentration, which shifts the Arctic from the state of, a highly compact piece of ice to smaller ice flows, which are now in free drift, which means they're responsive to the wind. The wind is the main driver. And as a result, we see an increase in this linear regression parameter for wind, an increase in this wind factor, which then, if the ice is more responsive to the wind, it will move faster. And so we see this free drift mechanism playing out averaged throughout the Arctic. But also, if we plot the slopes of each of these lines at each point throughout the Arctic, we see that spatially it also plays out. So we see overall, we have a negative trend in ice concentration, a positive trend in that wind factor, and a positive trend in the ice speed, or that free drift mechanism is playing out. But if we look closely, we'll see that regions where we have an increase in that linear regression parameter for wind are not necessarily regions where we have a negative trend in the ice concentration. And so we propose this free drift mechanism with non-local effects, whereby decreases in the ice concentration in these peripheral regions free up the ice in the central Arctic to become more responsive to wind, to enter that state of free drift, and then in turn increase in the ice speed. And these non-local effects are the reason that we think that application of this convolutional neural network and the explainable machine learning methods applied to that will be really good for diving into this problem to look at how some of these non-localities play out. So with that, I have shown you that machine learning is a useful tool to predict and understand ice motion in the Arctic. Thank you.
Thank you, Lauren. So again, if you have questions for Lauren for her presentation, please unmute or you could raise your hand. So Lauren, on I think it was slide 8, you have a map showing where the machine learning, the locations where your machine learning method was superior to, yes, that one. So could you describe what's going on in these marginal ice zones? I would assume that these are fast ice locations, and perhaps that the method doesn't matter, that these are locations where the sea ice doesn't respond to wind, and therefore either mechanism is as good. Is that what's going on?
Yeah. So one of the papers that this paper here goes into looking at the performance of these models in comparison to a bunch of different parameters in the Arctic. So how does the performance compare to ice speed? How does it compare to wind speed. A lot of, mainly, I think it's the depth in this region here, which is causing it to not be as responsive to the wind forcing. It's very shallow, very coastal. The island regions get in the way, so the wind doesn't play as much of a role over there. And then over here in this region, we have the very fast, the ocean current is playing a large role. And so the input parameters that we've built into our model are not picking up on that as much.
Okay, very good. Any other questions for Lauren?
Mike, I see you have a question.
Yeah, that was great, Lauren. I wish you had longer to talk. That was very interesting. I look forward to your paper. I do have a question. All right, so we've got a big old ice pack in the Arctic, and out near the edges, it's getting looser. But sort of in the middle or towards the Canadian archipelago, it's still very compact. It's still not in free drift. It's still got a lot of internal stress. So why do I care if I'm sitting in this very compact area? Why do I care about that it's getting looser out on the edges? How is that affecting it? I can't quite figure that out.
Like how are this question here?
Yeah.
That is a great question. I think that's what we want to dive into the explainable machine learning for on this particular topic. Like, where does it say it is important? And yes, it's not entering a state of free drift, but in this highly ice packed Canadian archipelago, but maybe in some of these regions out here, it is maybe not free drift, but it can become more responsive to wind. Particularly a thing that gets brought up a lot is the ice thickness. And I think that is a parameter that would be really helpful to look at when looking at these problems, because that can also determine how the wind is impacting that motion. So, yeah.
Okay.
I don't know if I quite answered your question, but
Thanks.
So there's a question in the chat from Julian. Julian, would you care to unmute and ask your question?
Yeah, I can try. Yeah, thanks a lot for the
Hello?
very nice talk. Yeah, the question is about the different features you put as an input of your machine learning or your linear regression. So if I understand it, you don't have only the wind, you have also the sea ice concentrations the day before, plus one of the features that I don't remember. I remember 3 features. So my question is about if you can comment about the relative importance. So not especially here, but the relative importance of each of those features for the quality of the predictions. Thank you.
Yeah. And normally I show that in this presentation. The wind is the most important throughout most of the Arctic. The importance of the wind dies off in coastal regions. And the importance of ice, we had persistence as one of the inputs, so the previous day ice velocity. The importance of that increases in those coastal regions, as well as the ice concentration becomes more important in those regions, both in the linear regression and the explainable machine learning.
And you never found that having the ocean also velocity could be important in some cases?
I think that, yes, it would be an important thing to add as a predictor. In this case, we wanted to build something that was from satellite and reanalysis products. So we didn't have the ocean. We started out with building it with inputs from climate models, but moved to inputs from satellite products. So yes, I do think that would be an important predictor, particularly in, the off the coast of Greenland and maybe the Beaufort Gyre areas like that.
Yeah, thank you.
Thank you.
Thanks. All right. So is it fair to say that with the technique that you applied here, that you essentially produced a model emulator for the sea ice response? My understanding of emulators is that there are different kinds. Some can apply machine learning, others are more statistical. Is that a fair assessment?
Can you elaborate a little? on what you mean? Like what?
I guess I was thinking of my experience with ice sheet models. Many people have developed climate emulators rather than using the expense of running the entire model
Right.
to represent the results.
Okay.
So here you've taken the relationship and developed a a machine learning system.
Mhm.
I guess the question is, what is the advantage of using machine learning as opposed to a statistical emulator for examining the sea ice drift?
Yeah, that's a good question. I don't know if I can quite answer that. I guess the reason that this work got started was to take that sea ice component of a dynamical model and replace it with machine learning, to see how well the statistics represented the system. But yeah.
Okay. Trevor may have a more reasonable question. Trevor, would you unmute and ask your question, please?
Yeah, I was wondering if you've thought about using like ensemble methods to improve the skill in those areas where the linear regression performs better.
Still different ensemble models, or
Something like a weighted average of the CNN and a linear regression where you give the linear regression more weight closer to the coasts or something.
okay. Yeah, no, we haven't thought of doing that, but that is an interesting to sort of get the best of both worlds. Yeah, that's an interesting point.
Thanks.
Yeah, thank you.
Thank you, Trevor. So with 10 minutes remaining, I was going to ask a question for both Zach and Lauren. We've been looking at machine learning to try to understand, the basic outputs of, or the processes that are represented in Earth system models. I'm recalling a presentation from AGU where a person was responding as to whether emphasis should be on the development of Earth system models versus the development of machine learning techniques. And it was kind of felt that that was kind of an inappropriate question, that the machine learning techniques should be used to advance our understanding of what the Earth system models are showing. Do you have a response to that type of inquiry? Zach, could I ask you that question?
Yeah, sure. Being at a modeling lab, that is discussed quite often, and I really don't see them in competition with each other. I really feel like hand in hand, our development with Earth system models and our development with machine learning go right together, and they can inform both one another. I think we're here at GFDL, there's been a lot of interest in model emulation and parameterization as we get to higher resolution because there's more cost associated with it. But it's fundamental to also develop machine learning. I mean, one could take that question about, how AI is advancing so quickly in numerical weather prediction. Of course, climate is, a different question, but training all that machine learning models requires the development of, observatory analysis data and Earth system models to train on. So I really see them going as they inform one another, and it's important to develop both. I don't know if that's a good answer, but the way I view it is definitely that both need emphasis and that they can help one another.
So the general understanding here is that we have a lot of models, and even here we make petabytes of output, but we don't have understanding of what the physical processes are on like an understandable scale, and that machine learning can help us better understand the output that we're seeing from Earth system models. Is that a fair statement? Either Zach or Lauren.
Yeah, I would say yes. I mean, given what both Zach and I talked about, it can, I mean, look at all of that data in a way that we can't look at it, and look at interactions and show us things that just the human brain can't do without this model to process everything. So I would say yes, that's an important.
Okay. Mike, you have a further comment?
I don't want to monopolize the conversation, but I like this, you know, this subject is interesting. I think both speakers, I thought I heard, you know, sort of a promise that we would learn something new beyond what we already know. And I don't know that I got the payoff. I think Lauren's map of the, you know, the non-local stuff was like a beginning of that, but I didn't quite, you know, understand it. But so I guess I would just ask both speakers, what have you learned new from this? What are the new relationships between parameters or non-local or whatever it might be? You know, what did you learn that was new from this stuff? And Vladimir tells me I'm getting too old.
Yeah, I can have an attempt at answer at that because even though I use, machine learning as a tool for some of my work, I am probably more skeptical than most people about the utility of machine learning. I said I'm interested in explainable machine learning, but what I found is that explainable machine learning is actually, it can be quite tricky and subject to our own bias. We could see a blob, let's say, over the Barents Sea, and I'll be like, oh, I know that that area is a real sensitive marginal isotone, but really the machine learning model might not be doing that. So these explainability tools can be also subject to our bias. So for me, I think the work I presented here is an example where we actually, didn't see a clear advantage to machine learning for evaluation. Other work that I've done not related to the Arctic, there have been more clear advantages, especially for signal to noise type questions. So to me, whenever I approach machine learning, I go about it very skeptically. That's how I view it.
And
Yeah, I
Lauren,
think so.
yeah.
Oh, yeah. Similarly, I think we went about starting the study like, oh yeah, we'll apply machine learning to understand this wind factor. And then we get to these machine learning methods and we're like, oh, there are like however many different explainable machine learning methods. And we apply each one, we get a different answer for every one. And so it's really looking at, okay, what does that mean now? So it really that comprehensive view of like, how can we complement this with physics and what we do know and maybe learn a little bit more from what's it's giving us.
Okay. All right. I would like to thank our two speakers, Zach and Lauren. Thanks so much for presenting. Tony, I think there's some end of the meeting housekeeping we need to get to.
Yeah, thank you, Richard. And I just want to echo thank you to Zach and Lauren for joining and for everybody else for giving us an hour of your day. With just the last couple minutes before the top of the hour, just wanted to share a couple things while I had you on the phone. First is that just wanted to remind everybody we're in the process of updating our biennial implementation plan. So this is going to outline our objectives and deliverables that groups like the modeling community practice are going to work on for the next couple of years. So I am going to drop a link in the chat. And at this link, you'll see a Google form that has more information on the plan as well as the process for submitting feedback. And I'll also just quickly pop up a slide that has a QR code that you can scan to get to this form as well. But as you can see on this slide, as it goes into full screen mode, perfect. The public engagement period for any input on the plan is going to be going through the end of May. And we're looking for any input, feedback on any research objectives and deliverables that should be continued, maybe with some adjustments, any that should be closed out, maybe they're completed, maybe we've got other priorities in terms of Arctic research we want to focus on, or anything completely new that should be added. And I did just want to note that any and all feedback from the community is super valuable, super important. The drafters will look at and consider any notes, any thoughts, any comments, questions that are submitted through this form. So again, we've got through the end of May and would love, for everybody to just take a quick look. And if you've got any feedback at all, we would definitely appreciate it and love to hear it. And then oh, go ahead.
Go ahead, Tony.
I think we might have been about to say the same thing, but that we would also just love if folks are available. The next Modelers Community of Practice meeting is going to be next week on April 4th. So I will drop a link in the chat for that event as well. But that is going to be held in tandem with the Permafrost Community of Practice meeting. And that is part of a series on Arctic biases in the US Earth system models. This one will be on permafrost carbon processes. So again, it'll be at this same time slot, 10 a.m. Alaska time, 2 p.m. Eastern time, doing quick mental math in my head as I am on Mountain Time. But again,
that's an hour earlier than this meeting. We'll start at 2 Eastern.
Oh, okay.
Yeah.
Oh, perfect. Thank you, Richard.
Okay. All right. So as Tony
off.
said, that's part of a series that we've had on biases in Earth system models in the Arctic, and so we'll have a panel of presenters as well as a presentation on permafrost and the carbon cycle over land over the land surfaces. Okay, and that'll be our next meeting. Again, I'd like to thank our speakers. I'd like to thank everyone for their questions and their input, and we'll see you again next time. Thank you.
Thank you, everyone.
Bye-bye.